All right, so today's class is going to be like a retro class because we're doing everything you've done in high school, or at least I hope you've done at some point before. We're talking about diagrams. But because you can't afford quick, right? So basically, we're going to do all of high school guys. We're going to do all of high school objects in 2.5 hours. Okay, quick. If there's anything to stop me, but I'm going to run under the assumption that guys, I'm just reminding you guys basically what it was. So the first thing we're going to talk about is what lights or how lights can behave. Right? We talked. There's going to be some that we know how they behave, but there's also going to be some that we don't know how they behave, and we're going to go through all that together. This here is kind of. I think you guys know the answer to this. I was saying that if you were to shine light on this opaque piece of material, whatever it is, with two slits in it, so nothing lets light through other than these two slits, then what you should see on the other side is two bands, right? And that would be true if light behaved like a particle, but not necessarily. It doesn't necessarily behave like a particle. And if you were to do this experiment, you would not get this result, right? So this would be actually quite wrong. And what happens is when you do the experiment, right? And I think we saw this together. The light travels through into the slits, and then as it enters the slits, you'll see this something called a diffraction pattern on the other side on the wall. All right, and that's one of the properties of light. The fact that it's a wave allows light to be diffracted, and that's the term that I want you guys to be familiar with. All right, so light can be diffracted. That's one of the properties. So if I were to say that this is my light source at this point here, it's shining in all directions, but the ones that I'm interested in are the ones that are going to go through this slit. What is it going to look like on the other side of this opening here? Is it just going to be like this? No, it's not going to be that. Does someone describe it for me, maybe? Is it what? Alba? Yeah, exactly. So it'll be like there's another drop of water right here going in that direction. So what you might have is something that looks like this, right? And that's diffraction. You want to ask me that? Yeah. No. In let's say in vacuum, you could say that's yes, maybe, but in reality, this dies off with respect to time. So eventually, it slows down and it stops. Oh, you're asking me like this point versus this point, let's say? Yeah, they would have the same energy. Yeah. Again, this is called diffraction. And later on, after we come back from the break, when we're going to do light in a more theoretical sense, we'll talk about something called diffraction patterns. And if I go back here, we'll be learning the equations to determine, first of all, how many of these lines are going to be, how far apart the bright bands are going to be, and how bright each band is going to be, right? So there'll be some math having to deal with that. It's quite interesting, but it's a bit more complicated. All right, so that's diffraction, and that's one of the properties of light that we're going to talk about, or that I just talked about. I'm not going into it in any more detail. You can see it's happening here with a water press, and you can see it happening here with light sources. It is quite obvious that it's behaving like a wave. Did I show you guys the video where the guy's making sound effects for movies with a slinky? No, it's quite cool. I'm gonna show you that to you guys. I forgot to check that. I'm gonna try this. We'll see how it goes. If it doesn't, it's gonna have to be speaker again.
So the trick is to take take a slinky and you suspend it. So the trick is to take a slinky and you suspend it from somewhere high above the ground, and you suspend it such that the end of the slinky is just sitting on the bottom of the floor. You don't want too much coiled up at the bottom, but it does need to be able to touch the floor. So with your slinky hanging from somewhere...
No, it's not fine. Alright, it's going to be crappy sound, guys, I'm sorry.
So the trick is to take a slinky and you suspend it from somewhere high above the ground, and you suspend it such that the end of the slinky is just sitting on the bottom of the floor. You don't want too much coiled up at the bottom, but it does need to be able to touch the floor. So with your slinky hanging from somewhere nice and high, all you need to make this sound is a way of amplifying the sounds that are coming out of the slinky, and there's two ways to do this. One is you can use a microphone. I've got mine connected to a PA system sitting behind me, but it's equally good if you have a microphone connected to a camera. You need to couple the microphone into the slinky, and I find the best way to do that is just to stick it in between the coils, like so. And then you can make your noise by just simply playing with the spring, and you can do everything from just giving it a tap or a flick, through to, if you want to make explosion sort of noises, playing with the spring, through to, if you want to make the Star Wars laser sound, I find the best way to do it is to just pick the spring up and drop it on the floor, and then just after you want to catch it to try and stop the echo. So let's do that. So I can do drop, catch, and there you've got your Star Wars laser sound. If you don't happen to catch the spring, you get an echo, like so. And so it's just a matter of catching the spring before you get your first echo. Like so. If you're not fortunate enough to have a microphone, there's another way to do this, and all you need is just a sounding board. One way to do it is to stick it onto the back of an acoustic guitar, for example, but if you're really on the fly with this, you can do it with something as simple as a foam cup. And so the easiest way to do this is just to jam the foam cup in between the coils somewhere, and the foam cup then acts to amplify the sound in the slinky. And so you can then get back your lace blaster sound, and if you're really fortunate and you have both, you can even use a microphone to amplify what comes out of the foam cup and get a slightly different sound to it. It's much more high pitch.
Sound effects experts who are creating those sounds. They're not slamming waves together or distorting waves to be able to make those sounds. They create the sounds, they record them, and then they use them for movie making. Like if you ever seen like like there's like medieval movies, like the person takes a sword out of their sheath and it goes shing. If you actually did that with the sword in the sheath, it wouldn't make that noise. But you need to have that for dramatic effect in movies, and so you need to kind of create that sound. And there is no there's a repertoire of like sound files that you can use, but those sound files had to have been created. So you have all these sound engineers who are creating them. And the reason why I'm showing you this is because this is an example of sound diffraction. All right, so we're talking about diffraction on light, but this is an example of sound diffraction. Another example of sound diffraction. This one is more for the biology oriented people. And this one's quite disturbing. Nah, I don't know.
There's many things about this place that are very unusual, and one of the things that
this person's a marine biologist, and they're studying seal. So again, excuse the crappy sound. I don't have speakers.
I find very fascinating is how quiet it gets. It's the quietest place. When the wind is down, when there's no wind, it wakes you up in the middle of the night because there's no wind and there's no sound at all. And if you walk out on the ice, you can hear your own heartbeat. That's how still it is. And you can hear the you can hear the ice crack, and it sounds like there's somebody walking behind you, but it's just the ice. It's sort of, these little stress cracks moving all the time, because we're actually, right here we're on ocean. We're not on solid ground. So, and you can hear the seals. You can hear the seals call, and it's the most amazing sound. They make these really inorganic sounds. They sound like, I don't know, Pink Floyd or something. They don't sound like mammals, they definitely don't sound like animals. It's really out of this world, I can say that.
You get used to a surface being solid, and you sort of think in your mind that you're on land. And then all of a sudden you'll hear the sound coming up through the floor. You'll hear the chucks and the whistles
And the booms.
and the booms that come, which are, you realize there's a whole world underneath you. The seals are moving and competing and fighting beneath you under the ice while you're here sleeping in a tent or working in a lab hut.
Notice something. Notice cold. It's really bloody cold. Look at the water. It didn't freeze flat. It froze in a wave. That means that the water wasn't calm when it froze. And for that to have happened, that means it was damn cold. Right? And so imagine you're these guys and you're up in the Arctic or the Antarctic and you're trying to listen to these things and you have to sleep there obviously because you have to spend months there with time studying this stuff. You're trying to sleep. These are the sounds that you hear, man. I find that totally mind blowing. I would never be able to do that. So again, that was another example of diffraction happening in sound. And again, we'll do examples of it with light when we get to it in a couple weeks. But that was a really applicable situation where diffraction is really important. So diffraction, that was the first one, the first property of light. The second property of light is reflection. And we're going to spend a little bit more time on this one. And we're going to draw something called ray diagrams. Do you guys remember doing those in high school or in previous years? Ray diagrams? Yeah. Okay. Essentially, it's basically drawing what happens to light when it reflects off the surface. And then we're also going to do refraction, so we're going to have a ray diagram for that. So over here, I have an incident ray. And an incident ray is an incoming ray. So if I were to say, for example, there's light coming from this light source here, right? That ray coming towards me, that's incident. And that light ray reflects off of me and goes towards you, that would be the reflected. Okay? So you need to know those two terms. It's quite important. What's important in reflection is this one law, and it's called the law of reflection. And that law states that the incident angle is always going to be equal to the reflected angle. All right, so I'm going to write that here. The incident angle is always going to be equal to the reflected angle. And this reflected angle, I wrote it as little r because I'm going to use big R for refracted. All right, so make sure you guys follow the same convention as me and you can make that difference. The angle that I'm measuring, if I were to use a protractor, for example, to measure the angle, it's not the angle with the surface here. It's the angle with the normal line perpendicular to the surface. All right. So make sure you have a note on that and that this is the angle that you're measuring, right? Because if you were to measure this angle, you would make some mistakes. It doesn't matter so much in reflection, but when we're talking about refraction, it's gonna change your answer totally, and you don't want that. You good with this? I got a question for you guys. Let me erase this so I can have more room. This is an incident ray. I drew it as a line, but in fact, it's pretty much a wave. So let's say I have my wave coming in like this. All right. And then it hits this surface. What is it going to look like when it bounces away? What is it gonna look like right? Is it gonna go under this? So I'm gonna give you two options. You guys tell me which one's the right option. I'll go with blue. We have this option. And we have this option. The blue and the green kind of look the same. But you guys get what I'm trying to differentiate here? What's the phase of the wave being reflected? Is it going to flip around, or is it going to continue the same way? So who says green? Who says blue? Well, what do you think is blue? I'm sorry? Okay, let me try a different color. Is that more obvious? So now it's green and purple. So who says green? Green? Who says purple? All right. Ron, why do you say purple? I see. Okay, so you're saying that it should like continue. Like if it were going, the next wave would have been below. So that's why you make this one below, kind of thing. I can tell you that your answer is right, but that explanation is not correct. All right, so the answer is the purple one. Let's get rid of the green one. Now the question is why? This is a ray that's being reflected. Shouldn't it do what you guys said? Because that's the intuitive thing, that it's being reflected and then it's going to go out the exact same way it came back in. No, not quite. Think of it this way. If this was a wave on a string, right, and we're disturbing the string by moving it up and down, and it travels to a certain point where the point is fixed, what ends up happening to the wave? Does it come back above or does it come back below? It comes back below. So it comes back on the opposite side that it hit it. And that would be exactly the same case here, because this is going to be a fixed end of a wave, and so therefore it's going to reflect off of it in the opposite phase. Okay. We're gonna write that. Reflect in the opposite phase. So when we're gonna do refraction later on, and we're gonna combine this idea with refraction. I want you to keep this in mind, right? So just remember that waves do this when they reflect. All right. It says here, remember that the angles are with respect to the normal line. Right? Sorry, I wrote over it. I wasn't expecting text to pop up. All right, there's two kinds of reflection. There's diffuse reflection and specular reflection. This is quite obvious if you think about it. This table here is reflecting it everything is reflecting light, right? The reason why you see anything is because that thing is reflecting light. If you saw a big black hole in the room, that would not be reflecting light, because that would be just absorbing the light. But otherwise, anything that's not a black hole reflects light to a certain extent. Even this black wallet, right? It's still reflecting light, just not a lot of it. Now the question is, what is specular and what is diffuse? We can talk about, are you able to see a reflection, a perfect resolved reflection, or are you able to see just light bouncing off? So in the case of this wallet, would it be specular or diffuse? So can you see your face if you looked at this in this wallet? You could? No. What about your table? It reflects light. Are you able to see your face in the table? No, you can't. How about the ground compared to the table? Which one is more specular and which one's more diffuse? The ground's a bit more specular, right? Because if you look carefully, you can kind of see the shapes of the light in the ground, but you definitely can't see the shapes of the light on the table. On the table, it just looks like a blur, right? And if we were to use, let's say, the screen of your laptop, and just if you have it in your hand, look at it at an angle like this, can you see other people's faces and resolve actual shapes in your screen? Yes or no? Yeah, so that would be an example of specular reflection compared to diffuse reflection. And it's very simple because if you were to look at this on a microscopic level, the waves are coming in, or the rays are coming in and reflecting using the law of reflection, right? Whereas here, the rays are coming in, they're still using the law of reflection to reflect, but this time they're bouncing off an irregular shape. So every single beam is going to have a different surface, that is a different angled surface on which it's going to reflect. So when they reflect, you're not going to get the same exact, like it's not going to be fidel, I guess. Well, how do you say fidel in English? It's not, what's that? Loyal? All right. So it's not the same loyal picture that's going to get reflected. The lights are getting reflected, but they're all going to get reflected in a different way. So you can't see the picture the way it's coming in. So far, so good? I'm not saying anything new, I hope. That was the second law. This is the third law. Not law, but third property of light. This refraction. So light can be diffracted, light can be reflected, and now light can also be refracted. And that means that it's being bent by light. And in order to understand that, we need to understand this concept of Snell's law. Alban, William, if you guys want to have a conversation, out of class, please, okay? The idea of Snell's law is that light slows down when it enters different media, right? Or speeds up. It depends on light has a speed of, what's the number around? That's sound. What's that? 12? 9? 300? 380? Yeah, 300,000 kilometers per second, or 300 million meters per second. And so that is the theoretical maximum light can travel in vacuum. That doesn't mean that that's the speed that light travels in other media, right? So if you have light entering water, for example, it'll actually slow down. And there's a way to determine what the speed is once it enters a new substance using this equation at the bottom, right? So I'll just do a real quick example. Do I have space here? Yeah, let's do an example here. So I have light coming in from the top here, like that, and going into this new medium. All right, and this medium is, let's say, water. This area is water. It's going from air to water. So that's air. This is water. And air, we're going to say, has something called an index of refraction of 1.00. Right? It's very close to how fast light travels in vacuum, in air. Water is going to have an n value of 1.33. Right? And we know that the speed of the speed of light in air is equal to 3 times 10 to the 8 meters per second. Okay? My question is to you, what is the speed of light in water? And in order to do that, we would use that first equation that I talked to you guys about. N1 V1 is equal to N2 V2. Can you calculate that for me, please? Oh, no, technically no. I mean, you wouldn't notice it because it's still very fast. But if you're talking about it on a mathematical level, then no. Your frame of reference is going to be different. Yeah. If it were going, you wouldn't be able to see light going faster than the speed of light in faster. And so let's say you're running in space versus standing in space, light still looks like the same. Okay. So what did you guys get? 2 times 2 point what? It's a constant. It's the speed of light. Okay. 2 points. Oops, I'm missing an exponent there. Times 10 to the 8 meters per second. All right. So light travels slower in water. Now we know that, and that's great. I want to ask you guys some questions. Does someone have a dry erase marker on their table that they can talk to? All right. Dry erase marker. All right. So here's my medium. And this is on top of this medium is air. At the bottom of this is water. All right. Let's scrap this. And I want to talk about some analogy. You're all running in a field of flowers, and you're holding hands. Everyone's having a great time. So this is a field of flowers, and your field is grass. Right? However, as you're holding hands, skipping down this field of grass, you're going to enter an area of sand. Right? So here you are. There's 19 of you here, but I'm just going to assume that there's only 6 of you because that's just more convenient. And you're all holding hands. So here you are. So ignore this for a second. Here you are, all holding hands, going in this direction. Okay? And as you get closer, so everyone's traveling at the same speed, right? Because everyone's running on grass. Everyone's running at the same speed. So every individual person has the same velocity, and so you're moving in a straight line. So at this time point, you're parallel to that. And at this time point, you're still parallel to that because everyone's moving at the same speed. All right. But let's say you get to this point here, where you enter the barrier. Is this person running at the same speed as this person? No, they're not. All right. So this person's running slow because they're in the sand and it's harder to run in sand. And this person's running fast. So if this person's running slow and this person's running fast, are they going to turn? In which direction are they going to turn? Are they going to turn? So if this is a normal line, right? Would they go towards the normal line or away from the normal line? Towards the normal line, right? Because these people are going to be running slower. So what's going to end up happening is you're going to end up facing a different direction once you've entered the medium, like this. And now you're going in this direction, let's say. Right? Now, once everyone's in the sand, then everyone's running at the same speed again, because now everyone is running slowly. And because everyone's running at the same speed, you're running straight again. Right? But now you're just facing a different direction. Let's say it was the opposite. Someone have an eraser on their desk? So let's say you're running from sand to grass. So now you're running from sand to grass, and these guys, they traveled, they went into the grass first because you're going on this angle here. And they're going to be traveling faster or slower now than these guys. These guys are going to travel fast, and while these guys are traveling slow because they're still in the sand. And so you're going to rotate in which direction this time? The other way. This time you're going to rotate the other way. So now you're going to have something that looks more like this. And you can see that the general direction of the wave front has changed. Right? And if you were to imagine this as light behaving like a wave, like that, right? That's how it would behave. And that's exactly what refraction is. If they were coming in straight down, they're coming in straight, would there be any bending? No, because everyone slows down or speeds up at the same time, so the direction doesn't change. Right? All right, perfect. Now we can use this idea of Snell's law to calculate this angle in which and this phenomenon is called refract. So you have, that was a crappy line. You have your straight line like that. Here's your normal line. And your incident ray is coming in like this at an angle of 45 degrees from air to water. And we said air is 1.00 and water is 1.33. Now the question is, at what angle is this going to come out on the other side? First of all, is it going to an area that's slower or faster? Slower. And so is it going to be towards the normal line or opposite from the normal line? Towards the normal line. All right, so we predict an angle that's going to be greater than or less than 45? Less than. Okay, so if you were to use Snell's law now, which is n1 sine theta little I is equal to n2 sine theta capital R for a refracted. And if you wanted to solve for the refracted angle, because that's what you need to know, what would you get? Did you have a question? What does? I believe it is I'm tempted to say the density, but that's too simple. I think it's the density. I can look into it. I'm not sure. So again, we're expecting a number that's going to be less than 45. And make sure your calculator is in degrees. 32? Can one other person confirm that? You guys got that? 32? All right, so that means this angle here, yeah, refracted capital R refracted angle is going to be equal to 32 degrees. All right, and that's what we were expecting. We're expecting it to slow down. This index of refraction, this number that water has, that is called it's called the index of refraction of A. And it's a characteristic property. You guys remember what that term is? Characteristic property? I don't know what it is. Or if you can give me another example of a characteristic property. Temperature of what? Fusion temperature or melting point. At what temperature does water melt? 0 degrees Celsius. The water is the only thing that melts at 0 degrees Celsius, right? And so we call that a characteristic property because for water, it is characteristic that it melts at 0 degrees. It is characteristic that it boils at 100 degrees. It is characteristic that it has an N value 1.33. Okay, and so should I talk about that now? No, I'm gonna wait for it a little bit. Everyone understands this? If I were to flip this around and say that it's going from water to air, would the angle be greater than or less than 45? It would be greater than, and you're expecting it to go somewhere in this direction. All right. So let's talk about something called the critical angle, right? And this only works if you're going from a slow medium to a fast medium, okay? So let's write that down. Slow to fast only. And this would mean that N2, or N1 rather, has to be greater than N2, okay? So I'm going to give you guys an example, and you guys are going to have to answer this for me. So I have my medium, same thing as before. It's going from, let's say, at an angle of 75 degrees. Okay? And it's going from an area of n is equal to 1.5 to an area of n is equal to 1.00. All right? Using Snell's law, I want you guys to determine what's going to be the refracted angle here. All right? It's going from from slow to fast. Are you going to expect the angle to be greater than or less than 75? Greater than, because it's going from slow to fast. You're gonna want it to go greater than. So let's do the calculation and try to figure out what that angle is. Can I get an answer for me? What does your calculator say when you try to do it? Yeah, it says it's error, right? And that makes sense. Mathematically, it doesn't make sense. I won't get into the math, but essentially, think of it this way: if I'm shining a light in this direction, right, and it's supposed to be an angle that's greater than 75, so already my angle is actually pretty great, and I didn't draw it correctly. 75 would kind of look like this, right? At some point, it's going to be at a maximum of 90 degrees, right? And beyond that, it can't go beyond 90 degrees. It doesn't make any sense. So that means there's a maximum value of 90 degrees. And at that angle, at whichever angle this incident ray comes in, that creates a 90-degree angle, we call that the critical angle. So that means we can say that the critical angle, if I have N1 sine theta I, is equal to N2, sine theta, I'm going to call this sine theta C for critical angle, N2 sine theta 90 degrees, right? Because it can't refract to an angle that's greater than 90 degrees. So let's just go ahead and figure out what that angle is, right? That is going to produce a 90-degree refraction. So what's the sine of 90 degrees again? 1. So that means we have N1 sine theta C for critical angle is equal to N2. And we can solve for the angle now. N2 over N1. And theta C is going to be equal to the inverse sine of N2 over N1. And in this case, if I wanted to plug in some values, it would be my critical angle is the inverse sine of 1 divided by 1.5. What do we get if that were the case? How much? 41.8 degrees. Yeah? So this means that at any angle greater than 41.8, the refractive angle is not going to work out. You're going to get an error on your calculator. So we call this the critical angle. And what ends up happening at the critical angle is that it reflects instead of refracts. right? You're not going to get any reflection here. You're going to get a pure, oh yeah, it helps out. You're going to get a pure reflection. And reflection follows the law of reflection. That means the incident angle is equal to the reflected angle, and it's going to be at 75 degrees again. No refractions happening, only reflection. Yeah. So 41.8 is the angle, right? It's going to be approximately there. It's going to be the angle that's going to produce a refracted angle at 90 degrees. Anything beyond that is going to give you reflection. Okay? So let's write that in a box. Any angle, any incident angle greater than the critical angle will result in total internal reflection. Are we good with that? So let's just do a real quick example here. So I have a ray that's entering air from water. I want to know at which angle I'm going to get total internal reflection, basically solving for the critical angle. Can you guys do that quick calculation? 48.8. Let's wait until everyone gets a chance to pick up their calculators. Who's going to answer? 48.75. I'm good with that. That means that any angle above that critical angle, I'm going to get reflection. All right, so my critical angle is equal to 48.75. Can someone try to rationalize for me why it has to be from slow to fast and it does not work if it's going from fast to slow? Try to think about that. I want an explanation. The question is, give me an explanation why it only works when it goes from slow to fast. Why doesn't it work when it's going from fast to slow? Yeah. Okay, then the answer has to do with the fact that it's going along the normal line. When you're going from fast to slow, does the angle get smaller or bigger? Smaller. So no matter what my angle is here, and it's a maximum angle of 90 degrees, because at that point, it's going to be in the other zone. So at maximum, I'm going to have a 90-degree incident ray, right, or 89.999999 degrees incident ray. But at any point, if I'm going into a slower medium, my angle is going to be smaller. It's never going to be bigger. So I can never reach that 90-degree refracted angle if I'm going from fast to slow. Okay? Yeah. Which direction? This way? Okay. Went from fast to slow. Okay. And you want to see if it goes like that? Never. Yeah. It's never even going to reach the normal. Because if you go at 90 degrees, or 0 degrees rather, it's going to be going straight through. There's no refraction. No. So remember here, if the wave is coming in straight down, it's going to go straight down. So let's say it's going at 1 degree, then it'll be a fraction of. Yeah. All right. This concept is actually quite important in precious ore. And you all are fans of diamonds, I presume. Have you ever seen a jeweler looking at a diamond through their little magnifying glass? You see it a lot in movies. They actually do that. And the reason they do that is to determine whether that's a real diamond or not. And how do you determine if it's a real diamond or not? Well, by looking at the total internal reflection. So these guys are so trained in looking at diamonds that just by looking inside it at a specific angle, if it reflects, then they know it's a real diamond. Because a diamond is actually the most refractive material that's translucent. Right, so out of all translucent materials, it refracts the most. So at a specific, it's going to have its own specific critical angle that jewelers are very accustomed to noticing, and they look inside to see if it's reflecting at that angle or not. And that's actually also what makes diamonds so precious to begin with, or what makes them so attractive, right? So imagine that you have the following situation. Here's your generic diamond. And here's your fake diamond. Real diamond, fake diamond. From now, they look exactly the same. But there is a fundamental difference in how light reflects and refracts inside. So a diamond has a very high index of refraction. If it has a higher index of refraction, then does that mean the critical angle is small or big? So remember the equation for a critical angle is equal to inverse sine of the incident angle or the critical angle is going to be equal to n2 over n1. So if n1 is really big, then my critical angle is going to be small. So that means if the angle is small, let's say the angle is whatever, 10 degrees from air to diamond, right? That means any angle beyond that is going to cause reflection. So here's light coming in. Is that light going to go in the diamond or is it going to reflect off the surface? Reflect, why? Too big? It's going to go in for sure because it's going from fast to slow. Okay, so it's going to go in for sure, right? But once it's in, any angle that it's going to try to come out of is going to reflect internally. So what you're going to have is this, and this, and this, and this, and this, and this. And eventually, no matter how you have it shaped, so these diamonds are shaped in such a way, they're cut in such a way to increase their brilliance. So what's going to mean is that, let's say this one escapes, because now you finally hit that rare less than critical angle, incident angle, and the light's going to come out. But if you were to send another ray here, because light's coming from everywhere, right? And they could all bounce internally and they're all going to come out at the same spot because the diamond is designed to let light out at a specific spot. And that's that shininess that you see, right? You're looking at a diamond and it's literally brilliant, right? Like it shines. And the reason it does that is because it collects the light and only lets it out in specific places so that you get this effect of shining. If you have a fake diamond, it would go in, it might do one bounce and then leave this way, right? And then another light comes in and leaves that way. So if it's not being funneled, if that light's not being funneled, because here the critical angle is too high and all the rays are coming out, it's not going to appear as shiny as a real diamond. right? And that's why everyone likes it. That's the history of why people are attracted to diamonds. It's shiny, so people want it, you know? And it's therefore, and even by like the idea that it's precious and rare and expensive makes it so that people want it even more. But the physics behind it is because of it. Make sense? And you guys have seen refraction for sure, other than in diamonds, of course. You've seen this phenomenon kind of happen where you look at a straw and a cup and it kind of staggers, or the fact that when you put a light in here, so this is actually called dispersion. I put it in here because it's like refraction slash dispersion. I'm going to talk about that in a second. Or spearfishing. Has anyone gone spearfishing before? You should try it. It's fun. No, I don't know. I've never tried spearfishing before. But imagine you're trying to catch fish with your hands. It's very nearly impossible. And the reason for that is because the fish always look like they're somewhere else compared to where they actually are. And the reason for that is because the light coming out of the fish makes it look like they're there, but in fact they're over here. So you're actually not even aiming for it properly, right? Next time you're standing on a beach and you're trying to spearfish, go stand next to the fish and go look at it straight downwards. Because if you're looking at it straight downwards, then you're back at the situation where there is no refraction, right? Right, so you would shoot your spear directly downwards. That's how you would do it. If you've ever seen like, I feel really old now. Do you guys ever hear of a show called Survivor? Because that was playing that was like early 2000s when I was in high school. You guys are barely alive. And there was this one guy, the guy who won the first Survivor. His name was, I can't remember what his name was. But in any case, the first Survivor, he was just like that one dude. He was always naked. He never wore any clothes. And he was out spearfishing. And you can see him like taking the spear and going directly downward. Whatever happened to that show? Is reality TV still a thing? Really? But like not like, well, that's not reality TV. That's just like, that's virtual reality TV. No one lives like that. Uh, um, I have a question for you. If I have an incident ray going from air to water or glass, it doesn't matter, back to air, what's going to be the angle coming in compared to the angle coming out? Why? I want a real explanation. All right, so let's do the calculation here. All right, and let's give it an example. We're going to say this is water at 1.33, this is air at 1.00, and back into air at 1.00. Right, so you're going to tell me that if this is 30 degrees, my incident ray is coming at 30 degrees. What's going to be this refracted angle? Can you guys look that up, please? Just do a calculation real quickly. Is it going to be smaller or bigger? The angle, is it going to be smaller or bigger than 30 degrees? Smaller than, yeah. 22. I'll go with 22. If I just zoom in here real quick. Actually, I'm going to put it on my line. If I zoom in here, what kind of, do you guys remember this from when you were in like secondaire when you had a parallel line and a parallel line? You have a line going through it. What could you tell me about this angle and this angle? They're the same angle. So that means that this angle here also has to be 22 degrees. All right. Remember it was like something like that. What was it? Alternate. That's it. It's funny how those things just stick with you forever. So that new incident angle is now 22 degrees. So you can figure out what the new refracted angle is coming out. And if you were to do the math, it would just be 30, exactly. The reason for that is because, let's say I have this situation. N1 sine theta 1 is equal to N2 sine theta 2 is equal to N3 sine theta 3. N1 sine theta 1, that's this area. N2 sine theta 2, that's this area. N3 sine theta 3 is this area. I'm going to ignore this bottom one because if this is equal to this is equal to this, that means that this is equal to this. right? And these both have the same index of refraction, right? This one has an n of 1, this one has an n of 1. So of course the angle is going to be the same, right? What does that depend on, though? How come that's true for this particular case? And is it true for this? I go from, let's say this is made out of glass, and it does this. Can you say that the angle going in here is the same as the angle going out there? Essentially, no, because this surface and this surface is not parallel, okay? So while it might work with this, it does not work with this, okay? By the way, you will need to know how to use a protractor for this unit. You guys know what a protractor is? You don't need to have one, but you need to know how to use one, okay? You didn't know it's called protractor? Okay. Anyways, a compass is the thing that draws a circle. Yeah. No, a compass is also a boussole. Yeah. All right. So we're talking about light being able to be refracted, but sound could also be refracted because, as you guys remember, light or sound rather travels differently when you're talking about hot air versus cold air. So here is a pretty interesting cartoon. This person's blowing the horn. In cold air, the sound actually doesn't travel to the dog. It actually travels above the dog, and this dog stays asleep. And in this case, if it was in warm air and the cool air is at the bottom, um, your sound would travel in a more downwards direction because of the way it's being refracted, and then you wake up the dog. Interesting because it matters. The acoustics and the temperature of the room and all that stuff matters in how sound is being perceived. All right. Lastly, we're going to talk about dispersion. So again, remember the first one was what? What was the first property of light that we did today? Diffraction. The second one was? Third one? Refraction. And this is the fourth one, dispersion. Okay? These are the four properties of light. Dispersion essentially is the same as refraction, all right? But that the speed of the wave of light is going to depend on its wavelength, all right? So that means that every single light particle of a different wavelength will travel at a different speed in the medium. So if I were to go back to this drawing here, so my white light comes in, everything is going in at the same speed, but once it hits this barrier, you can see that every different wavelength is refracting at a different angle. And that's because every wavelength is traveling at a different speed, right? And in this case, which one travels the fastest and which one travels the slowest? Does red travel fast or blue travel faster? So you're going from an area of fast to slow, right? And the slowest one is going to be the one that's going to refract the most. So which one is slow in this case? Blue, okay? So blue is going to refract more. So here, you can write that on this end, you can say that it refracts more. And here you can say that it refracts less. There are some things that I want to ask you guys to memorize from this electromagnetic spectrum, okay? This is something that everyone should know about this spectrum. And that is that you have this spectrum that is of different wavelengths, all right? And there are some here that are dangerous and not dangerous. If I were to ask you, are ultraviolet rays dangerous? Are X-rays dangerous? Are gamma rays dangerous? These are all super dangerous. So if they're dangerous, they're high energy, okay? So you can write that they're high energy. On this end, are they low energy then? Yeah, that means these are low energy. And infrared rays, they're harmless, right? Heat is an infrared ray. Radar, right? So anything that's a Wi-Fi cell phone signal. By the way, those of you who ever heard that your cell phone signals are giving you cancer, you can tell them that they're less dangerous than just regular visible white light. So these lights are theoretically higher energy than radio waves that are being emitted from your cell phone. Absolutely no evidence at all can ever be produced by that radio waves are dangerous. All right, so don't let that mumbo jumbo freak you out. You should not use your cell phones for other reasons, but that's just not one of them. And then there's microwave and all these other ones that are also not very dangerous. So these guys are going to be low energy. If I were to ask you to draw, yeah, yeah, like cell phone towers? Oh, those are still radio. They're pretty harmless. Yeah. There are electromagnetic. So then we're not talking about EM spectrum anymore. Maybe we're talking about magnetic fields and electric fields, right? And if we're to remember back in the other course, they're both harmless for the most part. Yeah. If I were to ask you to draw a high frequency wave versus a low frequency wave, which one would require you to expend more energy? So let me draw two waves for you. So here's my high energy, sorry, not my high energy, my low low frequency wave. The low frequency means that my waves are nice and far apart. All right. I expended a certain amount of energy to draw that. If I were to draw a high frequency, low wavelength wave, I have to draw this. So which one requires more energy on my part to draw? High frequency or low frequency? So we can also say, we can relate that here as well. That low, look how small the wavelength is here, right? 10 to the minus 14 meters, right, for one wave. That's going to be very high energy. So we have to remember that it's high energy for low wavelength, right? And here it's going to be low energy for high wavelength. I need you guys to memorize that, all right? If I were to say, if I were to talk about energy patterns of this spectrum, you should be able to tell me that stuff. Right? You should be able to tell me that these three are going to be higher energy than the visible light. You should be able to tell me that some of the more popular ones here are lower energy than the spectrum of light. Those are all fair game questions. One thing that's really interesting here is that AM radio waves, you guys know what AM radio is, right? AM radio waves are 10 to the power of 4 meters long for one wave. So think about that. One wave is 10 kilometers wide. That's crazy. All right. Here are some examples of that. This version, so light refracting at different rates for different wavelengths. Same thing for rainbows. That's all examples of this version. We have, what time did we start again? What time did we start? 10? 10:30. Okay. Not bad. An hour and 10 minutes to do half of this. Let's take a 10-minute break. Come back. Please come back on time, you guys. Yes, you. All right. The last slide on the previous PowerPoint was for you guys to fill out. It's not like a summary sheet for yourself to study with. Do that on your own for homework. I'll post the answers at some point. I don't know. We're going to move on to mirrors and lenses. We kind of already did that, but we're just going to have more detail on it. You guys remember drawing these in high school? We're going to do exactly that. We're going to do the curved lenses, curved mirrors, lens diagram kind of thing. All right? Like my little effects here. So low budget. I did it using PowerPoint. All right. So I put this in again just because we're going to need to use this concept that reflection is the reflection of light. I mean, it's pretty self-explanatory. I wanted to talk a little bit about conventions, and this is going to help you guys for the lab that you've done last week. Earlier this week. And what it means that something is a virtual image or versus a real image. And first of all, I want to define it by these two variables. So the di stands for the distance of the image. And when it's positive, do you consider that to be a real image or a virtual image? Yeah, so if it's positive, we consider that a real image. If it's negative, we consider that a virtual image. So let's write that down. What does it mean if the height of the image is positive? You guys remember that? It's not inverted, right? So it's upright, exactly. So if HI is positive, we call that upright. If HI is negative, it would be the opposite of that. It would be upside down or inversed or inverted. Inversed. And that's it. That would be more. What happens if the height of the image, the absolute value of it, we're ignoring the negative sign now. What happens if the height of the image is smaller than the height of the object? Do we consider that to be, is it magnifying or demagnifying? Demagnifying. That's not even a word. What's the actual word for the opposite of magnification? What? Frequency? Frequency. Let's go with shrunk. It's not right, but whatever. So shrunk. All right, and therefore, if I were to talk about magnification being greater than magnification being greater than 1 means that it's magnified or shrunk. Okay? Yeah, it's magnified. So in this case, if I'm magnified. Okay? There's one thing I want to remind you guys. This is like the most easily confused piece of information about this whole unit, is that when you're dealing with a mirror, the object should be, sorry, not the object, the image should be on which side of the mirror? Should it be on the same side as the mirror, or should it be on the opposite side of the mirror, behind the mirror? Right, so if we're talking about a mirror, should light be able to go through the mirror at all? No, a mirror is opaque, right? It reflects light. Doesn't light allow light to go through? Don't make that mistake, because in a lens or in glass or whatever, does light go through, yes or no? Yes. Does it reflect? No, not necessarily. All right, so we have to remember that those two key things. It's going to change your whole perception of this if you just always remember those two things. Okay, so we're talking about curved mirrors, right? And if you guys remember, each curved mirror has something called a focal point. You guys did that. You did that lab just a couple days ago, and each mirror, each curved mirror that you had its focal point. I want you guys to imagine a sphere, right? And this sphere is shiny like a mirror, right? And I cut it. Let's cut this one. I cut this one right here, like that. And that, if I take that piece that I just cut off, there's my curved mirror. Can you guys visualize that? Right? That means if this was part of a sphere, this sphere had a center. And that center is called the center of curvature. Okay? So I'm going to call it C, the center of curvature. Usually F is, if this was cut from a perfect sphere, F is always going to be between the mirror and C. So you would say that F is equal to C over 2. Or you can also say that 2F is equal to C. All right. And so in that case, in this picture, F would be somewhere along there. And that's the focal point that you're talking about when you're looking at a curved mirror. So it works the same way. So here, if the shiny part was on the outside, would it be a convex or concave mirror? Convex. And if the shiny part was on the inside of this sphere, we would call that concave. All right. But the focal point is calculated the same way. Make sense? So, if you remember about ray diagrams, there's a whole bunch of rays. here's an object that's emitting light, so kind of like a light bulb. So imagine this light bulb is shining. Which direction are the light rays going? Are they only going in that direction? Where are they going then? They're going everywhere, all right? So light rays are coming out in this direction, and this direction, and this direction, but we don't care about all of them. There's three that we care about the most, okay? The three that we care about the most are written here. Now I want you guys to memorize these because they're the same for curved lenses. All right, so the first one is the ray that goes through the focal point and parallel to the principal axis. By the way, this line here is the principal axis. Let me just draw it for you. This line here is the principal axis. Okay? Principal axis. So which one of these rays that I have drawn here, all right, that's why I gave these letters. That says A, B, C, D, and E. There's 5 of them here. Which one of these rays is going through the focal point? D. And if you notice, the ray that's going through the focal point hits the mirror and goes parallel to the principal axis. That one's mega important. No question? No? Which one is going through the center of the mirror and straight reflecting? See, exactly. It's going to the center of the mirror and is doing a regular reflection. Okay? And which one's going parallel to the principal axis and then through the focal point? Yeah, D. So parallel through the focal point. Okay? Here's what you need to remember. The image forms where the reflected rays meet. Let's write that here. So image is formed where the reflected rays meet. So let's look at my diagram here. I'm going to erase everything I drew in terms of the ABCDs. I'm going to point to something, and you guys tell me if this is an incident ray or a reflected ray. All right, I know that first only these guys are going to answer, but eventually I want everyone to yell out at the same time. If I point to something, you say reflected or incident. All right, so let's try this one. Let's try this one. Okay, good. So it's not where these guys that have an arrow going towards the mirror, it's not where they meet that's going to cause the image. It's really where the reflected rays meet that are going to cause the image. So if I were to look at all these reflected rays here, and look, they're converging onto one point. And that one point is where the image is going to be made. Okay? So let's do some practice on that. Yeah, I guess before we do that, before we do the practice, I want you guys to remember these couple of these formulas. So here, this is the equation for the curved mirrors and curved lenses. So if you remember it for mirrors, it's the same thing for lenses. Concave mirrors have a focal point that's positive. Okay? And convex mirrors have a focal point that's negative. I wrote that here, actually. I don't know why I wrote that again. Magnification is equal to negative of the distance of the image divided by the distance of the object, right? And it's also the same thing as the height of the image divided by the height of the object. Simple as that. I want you guys to think about something. What is the focal point of a flat mirror? Think about it for a few minutes. 2 seconds. You don't need minutes to think about it. What's the focal length of a flat mirror? So where? focal point is in the mirror, according to these guys? No. Come on, man. Someone else. Let's draw a circle. So here is a very small circle. Here's a really small circle. If I were to make this into a curved mirror, Alba, thank you. If I were to make this into a curved mirror, the curvature is quite curvy. If I took a bigger circle, and that's the center, and this is the focal point, then you can see that it's less curvy, right? If I were to take my car and try to do this turn, go around this circle, it would be a lot more difficult than if I were to take this big wide turn, right? If I had a really big circle, it would be even less curvy, right? And if I had a circle that was so big, right, that all I see is this, right? This is pretty close to a flat mirror, isn't it? Right? And so if that were the case, the focal point would be all the way over there. Yes or no? And if I had a totally flat situation, where would the focal point be? At infinity. So let's go back for a second. We have this equation, 1 over f is equal to 1 over di plus 1 over do. Oh boy. 1 over do. And we said that the focal point of a flat mirror is really, really far. So it would be essentially like saying this is 1 over infinity. 1 over infinity is equal to what? The limit as f tends towards infinity of 1 over f is 0. So you're going to have 0 is equal to 1 over di plus 1 over do, which means that, I'm just going to erase this big circle here so I have room, which means that it's negative 1 over di is equal to 1 over do. And therefore, negative di is equal to do. All right? That makes sense. When you look at yourself in a flat mirror, you appear, the distance that you appear towards the mirror is what the distance of your image appears into the mirror, right? So if I have a flat mirror like this, and here I am standing with my gigantic Uranian nose, right? You're going to see me at a distance equal on the other side, right? And this is going to be do, and this is going to be di. And it's always going to be negative. And we said that negative images are what? Virtual, exactly. So this image in a flat mirror is always going to be virtual. Yeah. I mean, if the mirrors are perfect, infinite, then you're perfectly parallel. Sure. Yeah. Have you ever gone to like?
When you go to the gym, you see yourself like.
Well, yeah, because there's a lot of mirrors. There's also the like you go to a clothing store and then there's a changing room with different mirrors everywhere, and you can like angle them. Yeah, you'll see them essentially forever. But the thing is, light dissipates after a certain amount of time, so it looks like you're looking at a very far away distance. Light doesn't reach that far. All right. Okay. So let's create some ray diagrams. We have to remember our 3 types of rays. You guys remember what they were? What's one of them? To the center of the mirror. And then what happens after that? Yeah, so that was a crappy line. Let me retry that. It goes towards the center of the mirror and then reflects at the same angle. Here's my first one. Let's try a different color now for this. So it's going to tell me a second. Through the focal point and what? Parallel. Okay, so let's go through the focal point. Oh, these drawings are really bad, eh? And parallel and through the focal point. Good. So if you were to draw this correctly, which I definitely did not do, all right, you should get that the 3 reflected rays converge to this massive point here. I mean, it shouldn't be a massive point if you drew this correctly. Using a ruler, you should be able to get that it all intersects at one point, right? So tell me a few things. Is my image smaller or bigger than my object? Smaller. It's inverted? Is it real or fake? Why is it real? It's in front of the mirror and it's supposed to be in front of the mirror, right? Okay. So let's write all that. So you're saying that DI is positive because it's a real image. You're saying that HI is smaller, or absolute value of HI is smaller than HO. And you're saying also that HI is negative, right? So this is shrinkage. This is inverted. What can you tell me about magnification? Greater than or less than 0? Why? What does it mean greater than 0? It's smaller, but that's not what the sign of magnification means. What is the sign of magnification? Inverted or not? So is it inverted? Negative. What about the absolute value of that compared to 1? Is it smaller than 1 or bigger than 1? Smaller, because you have to remember that m is equal to hi over ho. And if hi is smaller than ho, then you're automatically going to get a number that's smaller than 1. So it's going to be smaller than 1. All right. Let him do his thing. You guys are like off the hook today. No. All right, you guys do the next one. All right, it's the same principles, same 3 rays. You guys got this. This is a convex lens or a concave lens? Oh, convex. Yeah. How do you call this? Marker. Dry erase marker. Because it erases dry. So remember, it's where the reflected rays meet, where you're going to form the image. I'm going to draw the easiest one first. That's towards the mirror and reflect it. That's the easiest one. But does it go through the mirror? All right, so that's great. So we have another one going towards the focal point, but it doesn't reach the focal point. It goes towards it, but it doesn't reach it because on its way it hits the mirror. And if it hits the mirror, what does it do after that? Parallel. All right, great. That means it's there. And the next one is going to have to be parallel and then towards the focal point. But again, it can't go through the mirror, right? Because the light rays don't do that. So that means it's got to go in the direction opposite from it. And if you work your way backwards, that one should hit the focal point. Now the question is, where does the image form? Because look, the reflected rays are diverging. They're going away from each other. They're never going to meet on this side of the mirror. Where do they meet? Behind the mirror. So you're going to have to work your way backwards. So let's do that. Well, I'm just going to use red. So if you work your way backwards, computer's acting funny. Give it a second. Probably loading something. What's going on here?
Oh no.
All right. So if I work my way backwards from the reflected rays, they all meet here. That's perfect. That means I can draw my object. It's going to look like that. All right. So I want you guys to write down if it's virtual, if it's smaller than HO, if it's bigger than HO, what the magnification is. Try to write all that on this, what we did on the last problem, right? If I go back, what I did here for DI and HI and HO, HI here and here. I want you guys to do all that in the next example. All right, Danielle, sorry, man, you gotta go. It's what? Okay, try to focus here, right? So what's F compared to 0? What's DI compared to 0? What's HI compared to HO? What's M compared to 0? And what's M compared to 1? All right, what'd you guys get for F? Greater than or less than 0? What did you get for F? The focal point is positive or negative? Negative. What's DI? I hear a lot of different answers. It's hard to think that there are different answers from negative and positive. So is it positive or negative? Negative, because it's virtual. It's behind the mirror. It's not supposed to be there. Is this object, sorry, is the image smaller or bigger than the object? Smaller. So the absolute value is smaller than HO. Is magnification positive or negative? Positive, because it's right side up, right? What about the absolute value of magnification? Is it bigger or greater than 1? Bigger, smaller or greater than 1? It's smaller because it's sharp. Okay? There are way more scenarios where I can move these things around. I can move this object back here. If I were to go back to this object, I can put it on speed. I can put it between C and F. I can put it in front of F. I can put it on F. All that's going to generate different situations. Make sure you know how to do all those things, okay? If you don't, make an appointment with me, and we'll go over the ray diagrams for that. Moving on to flat mirrors, it's the same principle as what we just talked about. Now, every ray that's coming out of this has to be reflected with the law of reflection, right? So if I have a ray going in this direction, which I do, I just didn't draw it before. If I have a ray going in that direction, it's going to reflect at which angle? The same angle, right? If I were to draw my normal line, I would have an angle here, and it would reflect with a similar angle, a reflected angle that would be equal to this one, all right? And my image forms where all my reflected rays meet. So actually, where all my reflected rays meeting. So this one's going straight there and straight back. This one's going there and back. This one's going here and down. This one's going up and over there. So if I were to work backwards, because here they're all diverging, if I were to work backwards, they would all meet, and that's how you would find the image of a flat mirror. Okay? Yeah. Correct. Yeah, from the image to the mirror is the same thing as from the mirror to the object. For a flat mirror also. And it's also the same size, right? So here you can say that HO and HI are equal. HI is equal to HO. And you can say that negative DI is equal to DO. That's that one we mean. That DI is negative. And magnification is equal to 1. So let me ask you guys a question. When you do your makeup in the morning, everyone does it. Check out your pores. See if you got something stuck in your teeth. Okay. Makes your pores look gigantic. You're like, ugh, I gotta use one of those pore strips. Anyone use those? That's a girl thing. My wife, every time I come out of the shower, she's like, "Oh, let me get your blackheads," and she'll put this torture device on my nose, and then like plasters into your pores, and she rips it off, and she gets so much satisfaction from that. But it's just like I have like tears coming out of my eyes, so painful. But now I don't have blackheads. I've never looked at someone and said, "Wow, this person's got a lot of blackheads." Never in my entire life. I don't know. Maybe it's something I don't pay attention to. But oh, that's all you're doing, right? You're looking at each other and you're like, anyway. So what kind of mirror is it you guys look yourselves in? It's a concave mirror. But, hold on. How come when you use a concave mirror here, you're able to see an image that's smaller and inverted? That's craziness. You wouldn't use that mirror. It makes it smaller and it's inverted. It's useless. So what are the conditions? You go? Yeah, once you're closer than F, right, it starts to make it so that you're bigger and right side up, except the image is virtual in that case. All right, that's the only difference. I'll let you guys deal with the ray diagram, whatever shows up. All right. We're going to use this exact same principle to do thin lenses. I want to go through this part even faster, so stop me if I'm going too fast. If your lens was thick, right, it would do refraction twice, and it would be impossible for us to calculate any of this stuff. But we're going to assume that what we're talking about, everything is going to be a thin lens, and then the refraction only happens once. Okay, that's going to be our assumption, right? And this is why it's called a thin lens approximation. It's only approximately true. We have the same exact equations, all right? F is negative for a biconcave lens here. F is positive for a biconvex lens. So I'm just going to draw those out for you guys so you know which one's which. Biconcave, concave on both sides, convex on both sides. Okay? So again, remember that lenses allow light to travel through them. That's what lenses are supposed to do. So if you have an image on the opposite side of the lens, is that going to be a real one or a virtual one? So here's my object. Here's my lens. If my image is over here, is that real or virtual? That would be real, okay? Because the light is supposed to go through and form an image on the other side. It's the opposite of mirror. All right, so in this case, this would be a real image because it's on the opposite side of the lens. Again, it's different from the mirrors. Some convention here. If I want to draw a thin biconvex lens, I'll use this symbol, an arrow pointing in opposite directions here for biconcave. If you want to understand how we got those, imagine that this is the shape of a biconvex lens and that this is the shape of a biconcave lens. Okay? So we don't always draw the lens like a picture of a lens. Sometimes we just use the arrow notation. Okay? All right, so let's use those three rays again that we're supposed to use. So this is a biconcave or biconvex lens? Biconvex, all right? Go ahead, do it. Once you've done this one, do the next one as well. It's dead? I don't have another one, unfortunately. You can check with the tables. Someone keeps stealing them from this room. Does anyone find any more drivers?
So I was like the best year about it. So just not and we're in the class up. It was on. I like the big books that we had. Yeah, I didn't feel like one thing.
Yeah, sure.
I have to none of this, nothing. Fresh. Yeah. Yeah, imagine what? So one goes by yo, look, this is what it does. Virtual. Yeah, all you have to do is just follow the thing. And you know what's gonna form behind the mirror? You just I got my I had 16 on the guard. Not that cheap though. Yeah, you screwed everyone in the group like that. So that's why the average were like this. I went like this, yeah.
What course is that? What course is that?
Yeah, so the victim was regarding the end of the day.
You just said you cheated, though, right?
But
You cheated? Don't tell me that.
I didn't cheat. I didn't cheat. You can't I didn't change. It's like,
All right, so let's do the most obvious one first. If I have a ray going straight towards the center of my lens, what's going to happen to it? Is it going to reflect? It's going to go straight through, because remember, a lens lets light right through it. So right through. All right, here's where things get a bit complicated, because I have two focal points, right? It's a biconvex lens. There are two circular parts of it. So each circular part is going to have its own focal point. Now, the important part here is that if it's a biconvex lens, you have to memorize this. If it's a biconvex lens, it's going to converge light. It's also called a converging lens. All right, so you have to make sure that the light converges. So let's go with one of the parallel ones. Parallel. And so how do I choose which focal point to go to? It has to converge, so that means it has to go towards this one. Converging means that it takes light and funnels it. All right. Okay. The next one is through the focal point and then parallel. So I end up with this kind of situation here. And so my image is upside down. Oh, we're good. But I want you guys to pay attention to one thing, right? Look what's the difference between this image and the next image, right? So pay attention to everything that's digital here, not my own marking, right? So if I go like this and like this, what's the only thing I'm changing? Just this, right? And so, I mean, the fact that it's an up arrow here and a down arrow there made me do certain things. I have to know which different things I need to do when my arrows are flipped upside down. All right. So it's not the mirror or it's not the lens that's going to tell me what to do. It's really these two symbols that are going to tell me what to do. So go ahead and do this one. Now, considering that you know that this is a diverging lens. All right. So biconcave. Yeah, diverges light. The markers aren't great, eh? They're not erasing well. Okay, you guys keep doing that. I'll go.
one's behind the mirror. Yeah. And it's upside down. It's not mirrors, whatever the lens. Okay, I was.
Do any erase that during the physics stuff? I don't know.
Divergence. No, it doesn't. The one's behind. Oh shoot, a lens that wants it to go there. That's the real thing.
It's not supposed to form it in front, right? But hold on. Doesn't mean that it's not coming. I'm saying it's not supposed to in a lens, so therefore it has to be virtual. No, your A could be has to be here. Your A has to be here because if it's here, then why are you putting a lens behind the object?
Quelque chose qui sent, t'as mis l'incidence sur le fait c'est lui qui l'a mis. Ok, mais lui, ça va vers le focus. The reflective non, it's always the reflection. C'est ça, mais c'est celui-là. Non, parce qu'il can even comme ça. Oui, lui, il pense comme ça. Well, this is the reflection right here. Yeah, you're right.
It's not reflection, remember, it's refraction.
Mais c'est ça, mais c'est
I think Danielle might be right on this.
Oh yeah.
If you're done with this one, there's a third one after that. You can do that one as well.
Converge. The focal point like this, and then you have to reverse. That's a on the is it this one? J'ai actually été notre classe c'était 20 minutes. Spring break. Spring break. Quand t'es loin de toi. Yo, like 10 days. Like university applying. I would have to do that too. You're going to UBC?
All right, so I'm going to go over this question real quick. I just want to point your attention to one thing. Look how my rays are going, and they're all done. Once they hit the lens, they divert. And that's what I wanted to do. If I hit the lens, and then they converge, and I would have been drawing it wrong. The images here is going to be real or virtual? They're virtual because a lens is supposed to let light through, and the image is on this side. So it's going to be virtual. It's smaller, bigger, smaller, upright or upside down? Upright. Magnification is positive or negative? Positive, greater than or smaller than 1? Yeah. All right. Let's do it with this one. This one's a bit trickier because the angles are going to be pretty awkward. So let's do the easy one first. Always through the lens at the center. I've already messed it up. It's going to be parallel and then through the focal point. Okay. All right. And then the last one's a bit weird because the focal point is here. So that means I have to work all the way up and then go in that direction. So that means I'm going to be moving backwards. Like that. Okay, so I have to imagine that my lens is actually much bigger. All right, so I have to find where my image is. I have to work backwards to figure out where the refracted rays meet. So let's work here. There's a dotted line here. There's a dotted line here. There's a dotted line here. So my object meets over here. And this is what I have. Right? Is that virtual or real? Virtual. Is that larger? Yeah, it's pretty obvious. Let me ask you a question. What kind of lens is this? I want to go back to examples. Come on. Okay, so here it is. Here's my biconvex lens. My biconvex lens created a real image that was kind of smaller and inverted, right? But the same biconvex lens here gave me a virtual image and it was humongous, right? And all it mattered was where my object was. Here, my object was in front of the focal point, whereas here, my object was behind the focal point, right? If I were to look at something through a magnifying glass, you guys know what that is? And look, what situation is it? What kind of lens is it, first of all? The biconvex lens. Does it make things look bigger? Does it make things look upside down? No. So which situation would it be? It would be this situation, right? And that makes sense. When you look at a magnifying glass, let's say I wanted to look at Sammy with a magnifying glass. I'm not going to look at him from here. I got to go real up close to him. Put my magnifying glass. I need to make sure that he's within the focal point of my magnifying. What happens if Sammy was right on my focal point? It would what? It would be the same. I'll let you guys figure that one out. All right. You can draw the ray diagram on your own. There's something special that happens. Should we do more examples? Yeah, let's do more examples. All right, let's go through these questions 4 and 5, and then we'll call it a day after that, all right? They're numerical examples, so you're going to have to use the formulas. All right? So go to question 4 and then question 5. Once you're done, au revoir. See you guys tomorrow. Don't forget the lab. Don't forget you need your lab coat next week.